Hello everyone, my name is Jesus Aguilar Mijo. I'm going to present my thesis, multi-access computing for active video streaming. First, I will go through the motivation behind this thesis. After that, we will go through the multi-access computing concept and what's the meaning for us. Then I will go through the different research questions of this thesis. After that, we will continue with the research overview and the different elements and works of this thesis. I will finalize with the contribution and concluding remarks. Video streaming is the most widely used service in mobile network, with a 69% of data traffic share in 2022. On the other hand, edge computing is a key technology for 5G network that enables storage and computing power close to the final clients. This thesis aims to investigate how the video streaming process can be improved with the edge computing assistant. Now we'll see more in detail this multi-access computing concept. So basically it has several important characteristics. The first one is that it is owned by the mobile network operator that enables the deployment of third-party application at the edge. It also has computing power and storage available, so that enables to deploy mechanism that can support the video streaming. The location for us for the edge computing is co-located with the base station that enables low latency from 10, the range will be from 10 to 50 milliseconds. It is of course co-located with the base station. It has access to radio metrics through the radio network information service, which will provide better adaptation to the radio conditions. It also have access to all client requests, and therefore it can improve fairness. There is a common problem in the video streaming that the one client is not aware of what other user requests, and the edge can solve this problem. Now we will go through the different research questions. The first one is, how can network assistance for HTTP streaming be realized by edge computing functionality? So new mechanisms that leverage edge computing functionalities can be created and deployed at the edge node to guide and improve the video streaming process. The second research question is, how can radio access network and has client content information enhance bandwidth resource management? The edge is aware of its client requirements and needs, and also its radio network metrics. Therefore, it can coordinate the video streaming process among all the clients, improving the final QoE and the fairness among the clients. The third research question is how to perform radio metrics and client behavior analysis and prediction to improve the content delivery. So at the edge, we have the metrics that we need and the computing power to predict future metrics using these machine learning techniques that can be deployed at the edge. The final research question is, how can collaboration between different edge computing nodes assist the video streaming process? So we should not see this system as isolated edge computing, but there are more nearby neighbor edge computing that they can share resource, they can share computing power and storage among them. Now we will go through the different elements of this research. The first one is we investigate, we assess the lack of tool to test edge computing mechanism for active multimedia with the creation of edge computing and has a simulator. This work was named Angela HTTP Streaming and Edge Computing Simulator. The second element is like we investigate how to perform repackaging of media delivery formats at the edge to increase the bandwidth savings and improve the storage and cache efficiency. This work was named Dynamic Segment Repackaging at the Edge for HTTP streaming. We research also moving the AVR logic. Usually is client-based, so moving from the client to the edge to perform better adaptive decisions and distribute the content according to each device requirements and needs, achieving better QoE and fairness. This led to two publications. The first one is Ecas, Edge-Assisted Attention Scheme for HTTP streaming, and the second one is Ecas ML, Edge Computing Assisted Attention Scheme with Machine Learning for HTTP streaming. The last element is we propose, analyze, and compare different segment prefetching techniques with different usage of amounts and type of, of resources. This led to two publications. The first one is segment prefetching at the edge for active video streaming, and the second one is space, segment prefetching and caching at the edge for active video streaming. Now I'll go through this first publication, Angela, the simulator that focuses on test the performance of edge computing mechanism to support video streaming. It is written in Python, it's lightweight, and can be executed on different platforms such as Linux, Windows, or MacOS. One key characteristic of Angela is that it imports the radio layer data to reduce the simulation time without losing accuracy. So as the focus is on high layer, not on low layer, we don't need to simulate the physical layer as other simulators does. So for example, we compare our simulation with NS3, that is a really powerful tool, but again, it simulates the physical layer which is not the focus when we are testing edge computing mechanism. In that simulation, we see that Angela took 2.1 seconds and NS3 764. Again, this is because Angela import the radio metrics from a data set, so we have real values, but we don't need to simulate them. The edge mechanism that Angela the simulator has access to, it will be different metrics, like for example the radio metrics through the radio network information service, the player metrics, and all client requests. Also, different AVR algorithms are available to test. For the performance evaluation, there are customizable metrics to measure whatever you want to measure for your mechanism. For example, mean bit rate, the fairness of the stalls, and also has the QE, the standardized QE E2P1203 evaluation model. Angela was used to obtain results in these two different publications, the edge-assisted attention scheme and the segment prefetching and caching at the edge. Now we will go through a different element, that is the dynamic segment repackaging at the edge for HAS. So basically, in the classic scenario, we have the same content is duplicated and sent through the network. For example, the same video, if this user is using HLS, this one is dashed, this is smooth, and this HDS, we can see that the same video is sending multiple times, also storage at the edge multiple times, which also affects the cache efficiency. CMAF tried to solve this problem with just using one format, but the problem is the clients are not yet supporting CMAF, most of them. So our solution was use CMAF in the backhaul. So we have the bandwidth saving, we don't duplicate, we also storage once, we achieve better cache efficiency. And at the edge here is transmuxing operation is performing on the fly. So we convert the media file to the media format to the desired media format from the clients. For example, here it will be transmux into HLS, and you will send to the HLS client. We measure this extra operation, so the proposed solution also reduced the delivery latency if the edge has more than 1.64 times the computing power per segment than the origin server. This is expected because the computing power at the edge is lower than the origin server, but also serve less segments, way less. So this can even reduce the latency. Now we will go through another contribution, the edge-assisted attention scheme. We have two here, Ecas and Ecas. Here we have in this Venn diagram the different characteristics that they share. Both are on the fly, they are deployed at the edge, they are lightweight, they intercept and modify clients' requests, and they have access and use player metrics and radio metrics to perform their decisions. But Ecas support the client-based AVR algorithm, doesn't completely substitute it, take into consideration their request. It focuses on QE, but also the fairness, and it offers a clustering per subscription. This is, for example, for premium clients that use maybe some service provider has some premium clients that want more QE, and you want to provide better service to them. So with this characteristic, it can be done. Ecas, on the other hand, is completely substitute the client-based AVR algorithm and move the logic to the edge. It focuses on QE. It considers the screen display that is often ignored by other state-of-the-art solutions, and it has an LSTM-based model that will enable the adaptation to the current radio conditions, but we will see that in detail later. Continuing with EADAS, we can see that it improves the client-based AVR algorithm decisions. It's compatible with segment prefetching, so it will solve some classic radio throughput miscalculation of throughput-based AVR algorithms. We introduce an alpha value, so the service provider can manage the trade-off between fairness and QE. Here in the results we see the first one is with no EADAS, is the baseline results. Now when these results are with EADAS with different alpha values. So we see what the alpha value is really low, the fairness is at the top, is the maximum value, but in this graph, but the QE is lower with rather than higher alpha values where the QE is higher, but the fairness index gets low. So we can see a trade-off there. We test EADAS with different AVR algorithms, throughput-based, buffer-based, and hybrid-based. And we can see that in every case, the EADAS achieve better QE and better fairness. We can see clearly in the EADAS and in the throughput-based and SARA AVR algorithm, the increase in QE is quite remarkable, also in the fairness. Now we continue with the Ecas algorithm. The focus is on manage the trade-off among bitrate segment switches and install with 4 different parameters that we introduce in the algorithm. Also considers the screen display, which is often ignored. A long short-term memory network model predicts the best set of parameters for the current radio conditions. This means that these parameters that can be modified according to the service provider preference, but we introduce this LSTM model, so it uses the best set of parameters that will optimize this trade-off. At the end, it will achieve the best QE for the current radio conditions. So when the radio conditions change, these parameters will change, and we will obtain the best QE. Here we can see a little bit the player buffer. We determine 3 different areas. For example, in the low risk area, we will be more aggressive. In the high risk area, we will be more conservative. This is an example of the behavior, of the buffer behavior. Even though the radio conditions are not good, we can see here that the buffer size maintaining the medium risk area. It doesn't sometimes go to the high risk area, but suddenly fastly change to the medium risk area, and when the throughput is better, yeah, of course the buffer increase. Some results also with Ecas. As we can see here, we compare with different state-of-the-art AVR algorithm, buffers-based, throughput-based SARA, GBBA, which is another edge computing solution, and also SARA using EADAS. And we can see that the Ecas obtain the best mean bitrate, also the lowest number of stalls, excluding BBA because it's so conservative, it has 0. And at the end, which is the most important, it gets the best QE regarding the others. Now the last contribution is the segment prefetching and caching at the edge. Basically, segment prefetching is a technique that transmits the future video segment in advance, closer to the user, closer to the final client, to serve the content with lower latency. So here we will see different segment prefetching techniques with different usage of resources. The architecture we deploy here is the following. We have a layer 4 with all the different clients, the edge computing collocated with the base station, and we add another layer with we call it control edge computing nodes. What they do is they have a global indexing table that, for example, if a user here requests a video segment is not storage here, are not stored here, but maybe it's stored here. So this layer 2 control edge node will pull the segment because it has the information with this global indexing table. It will request the segment and send to this client through this layer 3 edge node. Now we'll go through the different policies. The first one is the most simple one, based on the last segment quality. So because usually the ABR algorithm doesn't want to change the quality because it will lead into segment switches that degrade the QA. We have the latest Q, just prefetch the last quality. LSQ plus will be prefetched the same, one above, one below, and then ASQ prefetch just all the qualities. Then we have prefetching based on a Markov model that, for example, each user will have its own Markov matrix. For example, here the quality one, we have a 73% of requesting the quality one again. So basically, this prefetching policy, what it does is prefetch the quality with the most probability of being requested. In this case, it will be again the quality one. Now we have prefetching based on transfer rating. So in this policy, a high quality representation is sent to the edge. Then the segment is compared to the desired quality that the user is requesting. For example, is sent the quality 4, but then the user requests the quality 2. So we perform that transmuxing. The advantage of this policy is that it assures 100% hit rate. This is the quality is always served directly from the edge node, so it will save latency. Of course, some transmuxing operation, some translating operation has higher translating times, but that can be deal with the buffer or the delay saved from delivering from the edge. Now we have the prefetching based on machine learning. This policy basically predict the future request of the ABR algorithms and then prefetch it at the edge. We use these 4 different metrics to make the prediction: buffer size, link bitrate, previous quality, and previous link bitrate. We do with the data set we collect data. We create a data set with a different combination of bit-tree ladders and ABR algorithms. And we test 5 different machine learning models, like for example, random forest, gradient boosting, ADA boost, decision tree, and extremely randomized trees. But the best one was random forest that achieved more than 90% of accuracy of predicting the correct quality. The last one is segment prefetching based on super resolution. So it's a little bit like the opposite of logic of translating. It will send a low quality representation to the edge, then perform the super resolution to the requested quality. So the bandwidth saving will be really high. We measure these operations and we deploy this policy, but the encoding time was a little bit high regarding the segment size. So actually this policy is not feasible until we can achieve lower encoding time. But we wanted to include this policy because in our understanding, it's really interesting, and in the future it is expected that we achieve lower encoding times, and therefore it will be really interesting policy. Now we can see some results here. This is the baseline with no segment prefetching. In red we have the QE, and we can see that, for example, ASQ that prefetch all the segment qualities achieve better QE, but also has really high amount of extra bandwidth consumption. Machine learning, on the other hand, we can see that achieve, again, really high QE, but maintain the extra bandwidth consumption really low. We will see some numbers after that, but yeah, all outperforms the baseline except the super resolution that, as I say, it had a big delay. So yeah, at the end, the best segment prefetching policy depends on the service provider preference and needs and results. If you want a straightforward implementation, LSQ is a good policy. Prioritizing QE, for example, with the trans rating or ASQ is possible. We have the conclusion that with the machine learning base, we achieve a good balance between performance and cost. Also, these policies are quite dynamic. It can be adapted dynamically to the current resources, so we can change between policies in the middle with multiple clients. We can provide one policy to one client or policy to another client and change dynamically. Finally, we will go through the contribution and concluding remarks. So this thesis investigates and develops novel approaches and tools to improve the content delivery for active video streaming services using the multi-axis edge computing. We have done several contributions through the course of this thesis that they are named here with the conference and journals. And I will do a brief summary. Angela focused on the research question number 1, as it has accuracy radio layer simulation, it has a really high time decrease regarding NS3. So this simulator that is used for testing edge computing mechanism was used in different publications. Then the dynamic segment repackaging at the edge that focus also in the research question number 1, and use CMAS in the backhaul and perform some on-the-fly conversion to the requested media content at the edge. It improves the cache efficiency and increases the bandwidth savings, and it can also reduce the delivery latency if we have at least 1.64 times the computing power per segment than the origin server. The edge-assisted adaptation scheme both target the research question number 2 and the Ecas target the research question number 3. It leverage the edge computing resources and available radio player and network metrics to perform better adaptation decisions. Both work on the fly, are lightweight, and including very low additional latency. IA does support and not substitute the client-based AVR algorithm and improve both fairness and QE. Ecas, on the other hand, focus on QE and manage the trade-off among bitrate, segment switching, and stalls. It also uses machine learning techniques to adapt to the algorithm parameters to the current radio network condition to achieve the better QE. We can see in the results that Ecas outperform BBA by almost 40% and other edge-based schemes such as GBBA by almost 20% in terms of QE. Finally, the segment prefetching and caching at the edge. It targets the research question number 3 and 4, and different segment prefetching policies with different resource utilization are proposed, analyzed, and evaluated. These policies use different techniques such as Markov prediction model, trans rating, super resolution, and machine learning. To provide some results, the machine learning-based policy regarding the baseline simulations increased the average bitrate by 46%, reduced the average number of stalls by 20%, and increased the extra bandwidth consumption by only 6%. Of course, this is a cost, but we believe it's worth it. But anyway, other policies will present a different combination of performance improvement and resource utilization. So therefore, the service provider can adapt to the needs. Thank you so much.